Alright, hello everyone. Okay, so in this video, I'm going to show you a simple example for using error-bound formula. Okay, alright, so let's get started. Now here's the integral that I want to solve. Now if you look at this function, isn't this the easiest function to integrate by hand? I mean, we can just use simple integration rules, right? So if you integrate x to the 4, what do you get? You get x to the 5 over 5, right? Now since this is a definite integral, you want to evaluate it at 1 and 0, and then you have to subtract. Now if you do that, what you get is 1 over 5. Now I did that fast, but I'm sure you can do that at home, right? So 1 over 5 means 0.2. So what does this 0.2 means? That means this is the solution. So if you integrate x to the 4 between x value 0 and 1, what you get is 0.2. That's the actual answer, okay? Alright, the next thing that I'm going to do is I'm going to use the midpoint rule to approximate this integral value. Now think about this. Really, we don't use any approximate integration methods, right? I mean, as you saw, the answer is 0.2, right? This is a function. X to the 4 is a function that you can integrate by hand, right? But anyway, let's just use an approximate integration method to do some error analysis. Okay, all right. Now if I use the midpoint rule, let's say with 12 subintervals, let's say n is 12, and if I use the midpoint rule, what I'm gonna get is, okay, so I did that at home. Okay, you can do it by yourself. The focus of this video is about the error bound. We will get there in a minute. But the answer, if you use midpoint rule, what you get is 0.1988. Okay, so this is the solution. This is the answer that midpoint rule gives. Now compare these two. 0.1988 is very close to 0.2, right? The real answer, actual answer is 0.2, and the approximated answer solution is very close to 0.2. I would say this is a real good approximation, right? Okay, now let's calculate the error. That means how off is the approximation is. So the error, to calculate the error, we can get the real answer 0.2, subtract what we got from midpoint rule, 0.1988. So the actual error is going to be 0.0012. This is the error. This is how much off is the approximation is. Now that's a good error. That's very small, 0.0012. I would be happy with this approximation. Okay, all right. Now where does this error bound formula fit in this whole scenario? Let's see. Let's calculate the error bound. Let's use the error bound formula. Okay, let's use this inequality. Now to use this inequality, we need a means the lower limit of the integral, which is 0. B is the upper limit of the integral, which is 1. N is 12, right? And this is the error bound formula for the midpoint rule. Okay, then we know a, b, n. All what we need is capital K. What is K? Now we know by the definition, K is the bound for the second derivative of the function, absolute value of the function. Okay, all right. Now function is x to the 4. Now first we have to calculate the second derivative, right? So the first derivative is 4x cubed. The second derivative is going to be, if you differentiate once more, you get 12x square. Now 12x square is the second derivative. Absolute value of second derivative is absolute value 12x square. You want to find the k value, okay, which is larger than 12x square, absolute value of 12x square. Now we can drop the absolute value because 12x square, no matter what x value you have, it's always positive. So you don't need to do double positive by taking absolute values. Okay, I mean, you can drop it. It's not necessary. It's anyway positive. Okay. Now you want to find the maximum of 12x square. Now 12x square, you can think, how do I know the maximum? Well, we don't need the maximum everywhere. I mean, for every x values, we only care about the x values that are between 0 and 1, because you are integrating between 0 and 1 here. Okay, so that's crucial. So the x values that we are working with are between 0 and 1. Okay, so between x values 0 and 1, what's the maximum largest of 12x square? Now, since 12x square is an increasing function, that means when you substitute larger and larger x values for x, it's keep on increasing. The 12x square value is going to increase. So when x is equal to 0, 12x square is 0. When x is equal to 1, 12x square is what? 12, right? When x is equal to 1. Then 12 is the largest value of the function 12x square between x values 0 and 1, right? So we can say 12x square is actually less than 12 for x values between 0 and 1. So k is 12. That's a valid argument, okay? Alright, k is 12. Now let's go ahead and use the formula, okay? Inequality. So error bound formula, let me rewrite that again. So it's capital K b minus a square 24 n square. So k is 12, b minus a is 1, right? B is 1, a is 0, 1 square is 1. So 1 square is 1, 12 times 1 is 12, right? So 24, n is I believe 12, so 12 square. So 112 and 24 cancel out and leave us with 2 here, and 2 times 12 square is 1 over 288. So what error bound says is that is what you get on the right hand side of the inequality is 1 over 288 is actually 0.0035. Okay, so what does this represent here? How do we fit in 0.0035? Okay, so the error bound said, let me write it here, 0.0035. okay, so this is what the error bound says, but we know actually the real error is 0.0012. What's the connection? Did you expect both of them to be same? No, okay, don't expect. Now error bound formula does not give you the actual error. It's a prediction. The prediction is, or how we read the error bound formula is that it says your error is guaranteed to be less than 0.0035. So this is the worst case scenario, the worst error. Now what's the actual error? 0.0012. That's smaller than 0.0035, right? So what error bound said is true. So error bound is a worst prediction, okay, worst case scenario. It's a prediction. Your actual error when you use the method is going to be definitely less than the error what error bound formula says, okay? So that's the idea here. Now think about this. X to the 4 was a function that we can really integrate really easily. But the point of using approximate integration method is to solve integrals which we cannot use basic integration rules, right? Or other integration rules. Okay, so really we never know how to find the actual error, because if you want to find the actual error, you want to know the real solution of the integral, which is something that you don't know, and that's why you use an approximate integration method. So you should be able to predict error. But error bound formula is something that you can really use, okay? Alright, so you know the function that you integrate, you can find the second derivative, so you can calculate the error bound formula value, and that error bound formula value will give you a prediction of the worst error. Okay, so that's the idea here. Now let's do something else. We know the midpoint rule gave us the approximation as 0.1988, and we know from the error bound formula the worst case scenario is 0.0035, right? Worst error. Now from here we can come up with something else. Now this is the midpoint approximation. What's the real value of this integral? We can say the real value of this integral is between, okay, 0.1988 plus 0.0035 or, okay, 0.1988 minus 0.0035. So what does this mean? Well, think about this. This is the value, the approximated value from the midpoint method. This is the predicted error. So the actual integral value, which we know 0.2, okay, pretend that you don't know it, okay, so the actual integral value should be, Okay, either 0.1988 plus 0.0035 or subtract 0.00035. Why is that? Well, we don't know whether this 0.1988 is an overestimation or an underestimation. Okay, now pretend that you don't know it's 0.2. Okay, so if it is an integral that you really can't solve, we don't know what midpoint says is either over or underestimation. So we don't know whether this error, so what you can do is, if you add the error to the approximation, then we can say we can find an upper bound. If you subtract, you can find a lower bound. However, the real integral value is between this upper bound and lower bound. So that's another thing that we can say from this using these error bound formulas. Okay, all right, so I hope it makes sense. Okay, so in future videos, in next videos, I will specifically focus on how to find this k, because that's something that students struggle with. We will take different types of functions and we will learn how to find k depending on the properties of the function. Okay, the strategy to find k depends on the property of the given function. Okay, so let's learn about that in the next few videos. Thank you very much. Bye bye.